Section: Introduction. In this section, we will discuss the challenges associated with training large language models. Training these models is a costly process in terms of time, energy, and computational resources. It involves a complex interplay of model architecture and training data to achieve high-quality results. Therefore, the typical approach involves conducting small experiments to ensure success before scaling up. This scaling process often relies on specialized scaling laws or established principles to optimize computational efficiency. Despite significant advancements in data and training techniques, one common practice in large language model pre-training is the use of the cosine learning rate schedule. The Chinchilla project highlighted that the cosine schedule achieves optimal loss only when the cycle length matches the training duration. However, it tends to underestimate the model's performance during training. This necessitates training multiple models of varying lengths from scratch to accurately assess training quality and scaling behavior, which is more time-consuming and restrictive compared to training a single suite of models. Our aim in this study is to reevaluate the necessity of the cosine learning rate schedule for training large models. Through numerous training runs, we demonstrate that a simple alternative of incorporating a cooldown period after a constant learning rate, as suggested in existing literature and utilized in recent models, can match the performance of the cosine schedule. We explore different decay forms and lengths for the cooldown period, which scale comparably to cosine and even outperform it with sufficiently long cooldowns. Additionally, we investigate stochastic weight averaging and a schedule-free optimizer as potential alternatives to learning rate decay, providing strong performance at various training stages. Our findings suggest that the complexity of research on training techniques and scaling laws can be reduced by eliminating the need to retrain models from scratch. We empirically show this by conducting a small-scale experiment on scaling laws that requires significantly less computational resources compared to previous methods. This approach makes scaling research more accessible and facilitates more frequent exploration of laws for data mixtures or novel architectures. Section Summary. In this section, we revisit the necessity of the cosine learning rate schedule for training large language models. Through various training runs, we show that a simple alternative of cooldown after a constant learning rate matches the performance of cosine, offering more flexibility in model training. By exploring different decay forms and lengths, we find that these alternatives can outperform cosine, simplifying the training process and making scaling research more accessible and cost-effective. Section: A different route. Constant learning rate with cooldown. In this section, we explore a different approach called constant learning rate with cooldown. We aim to understand why the cosine schedule with a single cycle is effective for training large language models, LLMs. The cosine schedule strikes a balance between maintaining a high learning rate and gradually cooling down the model as training progresses. An alternative approach is the constant learning rate with a cooldown phase. This method involves keeping the learning rate constant for most of the training process and only reducing it in a short final phase known as the cooldown phase. The cooldown phase typically involves the learning rate decreasing linearly to zero, similar to how it increases during the warm-up phase, resulting in a trapezoidal shape overall. This schedule, referred to as constant LR plus cooldown, offers the advantage of not requiring the number of training steps to be predetermined. This flexibility allows for observing the model's behavior and deciding when to stop training. Additionally, training can be resumed from a checkpoint before the cooldown phase, enabling continual learning. During the cooldown phase, adjustments can be made to the data mixture for fine-tuning. Experimental comparisons between the cosine schedule and the constant LR plus cooldown schedule show that they perform similarly well, with the latter being less sensitive to variations in the learning rate. Various functions describing the cooldown shape, such as cosine, square, and square root shapes, have been investigated, with some outperforming the linear cooldown. The optimal number of decay steps during the cooldown phase is crucial for maximizing performance, with around 20% of total training steps being a good choice for smaller models. During the cooldown phase, a smooth drop in loss occurs for both training and validation data, aligning with the decrease in learning rate. This suggests that the model transitions smoothly to a connected minimum in the loss landscape during the cooldown phase. Further analysis reveals that this smooth drop in loss also occurs when interpolating between model weights before and after the cooldown phase. This indicates that decaying the learning rate leads the model to descend into a connected minimum in the loss landscape. Section Summary. In this section, we explore a different approach called the constant learning rate with cooldown, which offers a balance between maintaining a high learning rate and gradually cooling down the model during training. This method eliminates the need to pre-specify the number of training steps, allowing for flexibility in observing model behavior and making decisions on when to stop training. By introducing a new cooldown function that outperforms linear decay, this approach achieves comparable or better performance than the cosine schedule, especially when the cooldown length is optimized to be less than 20% of the total training steps. Section: Do we even need to cool down? In this section, we demonstrated that using a constant learning rate, LR, with a brief cooldown phase can be just as effective as using a cosine decay. Ideally, we would prefer not to have any decay at all and aim to have an optimal model at any point during training, even for extended periods. This would help save computational resources and time. We explore two potential approaches: weight averaging and a schedule-free optimizer. For stochastic weight averaging, SWA, we found that averaging the weights within fixed windows during training can reduce noise and improve generalization. We experimented with different window sizes and found that windows below or at 2,500 steps are optimal. We also compared SWA with an exponential moving average, EMMA, and found that SWA performed better. Our experimental results showed that SWA, when combined with a constant LR or a cosine schedule, significantly improved performance. While SWA did not reach the same loss values as cooldowns at intermediate steps, it provided a compelling approach to training strong models without the need for a separate decay phase. Regarding the schedule-free optimizer, SFO, we found that it does not require a decreasing LR schedule, making it suitable for continual training. However, the choice of momentum parameters significantly impacted its performance. SFO performed well with specific momentum values but was matched or outperformed by the cooldown schedule in our experiments. Our investigation highlights the effectiveness of using a constant LR with a short cooldown phase for training large language models, LLMs. We emphasize the importance of scaling laws in optimizing compute resources and model performance. By utilizing methods like cooldown schedules and weight averaging, we can conduct scaling experiments more efficiently and flexibly, reducing the required training runs and computational costs significantly. Section Summary. In this section, we explore the idea of whether we really need to implement a cooldown phase during training. By experimenting with stochastic weight averaging, SWA, and a schedule-free optimizer, SFO, we aim to find alternatives to the traditional cooldown schedules. Our results show that SWA can enhance model performance without the need for a separate decay phase, offering a cost-effective approach for training. Additionally, SFO, while not fully schedule-free, presents a promising alternative but is outperformed by the cooldown schedule in our experiments, showcasing the importance of exploring different optimization strategies for efficient training of large language models. Section: Limitations. In this section, we conducted experiments on models ranging up to 360 million parameters, training them on up to 10 billion tokens. We observed consistent trends across all scales, although behavior may vary at larger scales. The method of using a constant learning rate followed by a cooldown has been successful for larger models. Instabilities caused by a high learning rate during training can be reduced. We believe there are no fundamental limitations to this method at scale. Additionally, we focused solely on training or validation loss, even though downstream tasks are the ultimate metric of interest. While these tasks often correlate with the loss, further research is needed, especially when considering different data mixtures during the cooldown phase, which is beyond the scope of our study. Regarding related work, The cosine decay schedule was initially introduced for cyclic schedules in vision tasks to avoid poor minima during training multiple epochs. For language models, the cosine schedule with a single cycle is commonly used for training, with some exceptions. Recently released models are exploring alternatives such as stepwise schedules or a constant learning rate followed by a cooldown. Previous studies have shown that a linear decay can slightly outperform the cosine schedule. Weight averaging, where past iterates' weights are averaged, has been known to aid convergence. Different averaging techniques have been beneficial for generalization in deep learning models. In the context of language model training, some studies have shown that averaging weights can improve model performance early in training. However, the relationship between weight averaging and computational efficiency has not been thoroughly investigated in scaling experiments. Scaling law experiments for neural language models have been established by training a range of models with a fixed token count. Recent works have improved the performance of smaller models by training beyond the optimal point, considering lower inference costs. Studies have highlighted the impact of data repetition and quality on scaling behavior, suggesting that scaling laws should be updated more frequently. Our focus is on conducting efficient experiments for scaling laws.